Hey, what's up everybody? This is Back to Live, and today we're going to learn what are transistors and what are logical gates, alright? So a transistor is basically, right here, a mechanism that allows electricity to either flow or not to flow. It does this by either increasing or decreasing the resistance. Increasing the resistance doesn't allow electricity to flow. Decreasing the resistance does allow electricity to flow. So a transistor can be created by using three wires right here. So one wire is connected to the source, the other one to the drain. Basically, electricity flows from source to drain. All right. The third electricity here controls the transistor. So if a gate has a logical Boolean value of 1, it allows electricity to flow. So resistance is reduced. If a gate has a Boolean value of 0, it does not allow electricity to flow. So basically, this increases the resistance, not allowing the flow of electricity. All right. So actually, right here we have a different version of a transistor. So as you can see, it just has a circle over here. It just does the inverse or the opposite of this gate or this transistor. So if the gate has a Boolean value of 0, it does allow electricity to flow. If it has a Boolean value of 1, it does not. All right, so simple. So now let's get to logical gates. All right, so let me just show you an example of how to create one of these gates using the transistors. All right, just so you can see how one would work. So right here we have the inverter gate, right? This one. We have the inner workings of the inverter gate. So what does the inverter gate do? Basically, if you give it a 0, you want an output of 1. If you input a 1, you want an output of 0, right? So let's look at this example. If we give it a 0 input, what happens? This gate opens, this does not, all right? So because this one's open, the voltage flows, output is positive voltage, meaning it's a 1, right? So we have a 0, you have output of 1. So what happens if you input a 1, right? This one closes, this one's opens, all right? So you have an output of 0 volts, all right? So 0 volts basically means a 0, right? So 1, output 0 volts, 0, right? So that's how a inverter gate works in the inside. That's how the circuitry works. So these are all of the logical gates. You don't need to understand the inner workings, the circuitry of it, but just know that inside of all of these logical gates you have transistors, right? So the NAND gate, or the not AND gate, is basically represented by a D with a circle. The NOR gate, not OR, is represented by like this spaceship and a circle. Inverter gate is represented by a triangle, right? NAND gate, just basically a D, OR, spaceship, let's see. And as you can see, the circle is missing in these. So whenever you think about circle, just think about the inverse of it, right? And right here we have a special one. It's called a exclusive OR gate. It's basically the OR gate. No, it's basically the OR gate, except that whenever you give it an input of 1 1, right, 2 1 1 inputs, you get a 0 instead of the usual 1, right? So if you get the OR gate an input of 1 1, you should be getting a 1, right? So let me just show you how the truth table for all of these work. So what's the truth table for AND? That should be quite simple. Just basically, if both inputs are 1, you get a 1, right? But otherwise you just get 0. All right. So what's the truth table for the OR? Basically, if there's a 1, you have a 1, right? It's only 0 when you have 2 zeros, right? So what's the truth table of not AND? The way I look at it is just the inverse of AND. So whenever you see a 0, just put a 1. There we go. 1 should be 0. All right. So now what's the truth table for not OR? It's basically the inverse of OR. So whenever you see a 0, put a 1. whenever you see a 1, you put a 0. All right. So now what's the truth table for not OR, exclusive OR or XOR? It's basically the same thing as OR, right? Except that whenever you have a 1 1, you just have a 0 instead of the usual 1, right? So now that we know the truth table for all of these symbols, right? Let's do a simple question. So right here, we have create the exclusive OR function, right? XOR, using NAND, NOR, and inverter gates. So using 3 gates, right? 3 of all the gates we have, how can we create the exclusive OR gate, right? So using these 3 gates, how can we create this one, right? So now let's see here. So how do we create this gate? So the way we create this gate is by having a function that has the exact same truth table as the XOR gate. All right. So how can we create one? Right off the bat, I see right here we have 2 1 1s, right? For these two, for this function. If we were to have an AND function connecting these two, this will have a 1 value. These 2 1 1s will have 1 value, and the other ones will have a 0. So let me just write it out. OR and NAND, right? So 0 0. What's the AND of 0 1? 0. What's the AND of 1 1? 1. What's the AND of 1 1? 1. What's the AND of 1 0? 0. All right. So as you can see, these two truth tables are the same. Therefore, if we create this, we will create an XOR gate, right? So right here, I created the representation of the XOR gate using the symbols, right? Our logical gate symbols right here. So let me just place the truth table right here so you guys can see. Actually, can't see here. So let me just quickly tell you all what's going on here. So right here, I basically have a NOR gate, right? This is NOR. This is an inverter. And this is a NAND gate, right? NAND is also a NAND. And this is inverter. All right, so let me just say what's going on here. What's NOR? Not OR. What's the inverse of not OR? Basically NOR. Basically OR. So all of this is just OR, right? What's NAND? What's NAND? Not AND. What's the inverse of not AND? Just AND. So this is AND, and this is not AND, right? So just like in our truth table, we have OR, AND, not AND, basically equals XOR, right? So now let's just quickly run down this entire gate, give it an example. Let's say we have 0 0 as our input, right? What's the NOR of 0 0? NOR of 0 0, 1. Okay, 1. Inverse of 1 is 0. So let's give it a 0 right here. All right, what's the NAND of 0 0? NAND of 0 0. 1. Right, 0 0. What's the NAND of 0 0? 1. And there's a 1 over here. All right, what's the NAND of 0 1? 0 1. NAND is a 1. What's the inverse of 1? 0. Output is 0. All right, so if we give a 0 0 into this entire gate, right, 0 0, we get a 0, right? Boom, it works. All right, just let's do this. Let's do this one more time. Instead of a 0 0, let's give it a 1 0, right? So this should be 1. So what's the NOR of 1 0? 1 0 nor 0. Inverse of 0, basically 1, right? So this should be 1 over here. So now let's look over here. 1 0, right? 1 0. What's the NAND of 1 0? 1 0 NAND 1. Alright, it works. So 1 1. What's the NAND of 1 1? 1 1 NAND 0. What's the inverse of 0? 1. So the output is 1, right? So if we give it a 1 and a 0, 1 and 0, the output is 1, right? So there we go. It all works out. So now that is it for today. Thank you all for watching and have a great rest of your day. Bye-bye.